Hi everyone. In today's video, we're going to continue our discussion on aromatic compounds, and this time we're going to really focus on activating and deactivating groups. It's my hope that by the end of this video, you will be able to start getting a sense on how to predict the major products for electrophilic aromatic substitutions that involve monosubstituted benzene rings. You'd be able to explain why some groups are considered activators and some groups are considered deactivators towards electrophilic aromatic substitutions. And then you would be able to explain why generally activators are ortho-para-directing and deactivators are meta-directing in these types of reactions. So recall from our previous work that you can take benzene and treat it with a variety of electrophilic agents, especially in the presence of strong Lewis and Bronsted acids, and you can afford an electrophilic aromatic substitution. For example, you can take your bromine or your chlorine and you can treat that with iron 3 bromide or aluminum chloride, respectively, in the presence of benzene, and you will get the brominated or the chlorinated benzene product. But in all these reactions, we'd essentially just started by focusing on benzene as is, and then we started to add on specifically to that particular compound. But what if you wanted to do an electrophilic aromatic substitution on a benzene ring that is already substituted? So for example, if you can take toluene and you react that with bromine in iron 3 bromide, the question is what kind of product are you going to get? And specifically, what regiochemical outcome of your product are you going to observe? So we're going to begin our discussion with the concept of activators or activating groups. And we're going to use our nitration reaction as our key reaction in comparing reactivity when we're dealing with activating and deactivating groups. So for example, take benzene and treat that with nitric acid in the presence of H2SO4. You're going to get your nitrated product as we've seen in the past. But now let's compare this reaction with benzene with the same type of reaction with toluene this time. First of all, we know from experimentation that the nitration of toluene occurs 25 times faster than the nitration of benzene. So that's our first indication that the reactivity here is different between these two different molecules. And secondly, there are three possible constitutional isomers of your product that you should be able to think about. One in which the nitro group is ortho to the methyl group, one in which the nitro group is para to the methyl group, and the other in which the nitro group is meta to the methyl group. However, we do not see all three products in equal amounts. In fact, we do see a distribution of products in which the ortho and the para products are more significantly produced than the meta product. In other words, we call this reaction regioselective because although multiple product constitutional isomers can be formed, only one or more, but not all of them, are formed to a large amount. Okay, so now let's consider the rationale for the rate and selectivity difference between benzene and toluene. So recall that this reaction is inherently an electrophilic aromatic substitution, where your benzene or your toluene group is your nucleophile in the reaction, and your HNO3, your nitric acid, is your electrophile in the reaction. And then given that we know this, therefore, the more nucleophilic or the more electron-rich that benzene or aromatic ring is, the faster the electrophilic aromatic substitution. So now what we really need to do when we're thinking about why toluene is faster than benzene, we really need to compare the nucleophilicity or the electron richness of the benzene ring in benzene versus toluene. So the question here is which is more electron rich, benzene versus toluene? And the key thing to remember here is that alkyl groups donate electron density via induction. So if you think about a dipole moment where your alkyl group is on one side and then your benzene ring is on the other side, there's going to be a dipole moment moving towards the benzene and away from the alkyl groups, which is to say that alkyl groups are inductively donating. And because alkyl groups are inductively donating, that benzene ring is going to be more electron rich in toluene than in your parent benzene compound. And so therefore we would say that the alkyl group essentially activates your benzene towards electrophilic aromatic substitution. This is why we call these types of groups activating groups, because they make that benzene ring more electron rich and in other words more nucleophilic, and so they become faster towards electrophilic aromatic substitution reactions. Okay, so that's it for the rates. Now let's look at why the reaction is selective. To rationalize for selectivity, we can actually look at the rate determining step, which is the formation of your sigma complex in this reaction. Okay, so consider the attack of the nitronium ion by your toluene. There are three possible locations in which the nitronium ion can add to the aromatic ring. And this would be either the nitronium add to the ortho position, to the meta position, or the para position. So let's consider the sigma complexes for all three of these possible pathways. So here's a sigma complex in which the nitro group adds to the ortho position on that benzene ring. And then here's a sigma complex where the nitro group adds to the meta position on the benzene ring. And then finally, here's a sigma complex in which the nitro group adds to the para position of the benzene ring. So you should be able to draw out all of these sigma complexes based off of your previous work in looking at the mechanism of these types of reactions. But notice that where you add your nitro group on the benzene ring actually dictates the identity of the carbon that has carbocation character. But what I want you to do is focus on two of the resonance forms, one from the ortho sigma complex and the other from the para sigma complex. Notice that in these two complexes, that carbocation character is placed on the carbon bearing that alkyl group, which we have already established is inductively donating. And so given that your sigma complex is really electron deficient, anything that can help to stabilize that carbocation character is going to be incredibly helpful in stabilizing the sigma complex, which will make the reaction go faster under those pathways. Which is to say that the sigma complexes leading to the ortho and the para products are especially stabilized by your toluene methyl group, where you do not see that in a meta sigma complex. Notice in this meta sigma complex, the positive charge is never at the carbon bearing that particular alkyl group. Therefore, more of the ortho-para products are going to be formed in this reaction. And so, because of this selectivity preference for the ortho and the para products in your nitration of your toluene reaction, we call the toluene alkyl group, so that methyl group or alkyl groups in general, as ortho-para directing. So they direct the electrophilic aromatic substitution at the ortho and the para positions on your aromatic ring. Okay, so we've established that toluene undergoes electrophilic aromatic substitution with HNO3 faster than benzene, so it's about 25 times faster, and that's because the alkyl groups are activating groups in this particular reaction. We've also established that it's ortho-para directing, so you get more of your ortho-para products than your meta products. Now, let's compare this same nitration reaction with the reaction with anisole. Remarkably, this nitration reaction is 400 times faster than the nitration reaction in toluene. And just like your toluene reaction, you get more of your ortho-para products than your meta products. So we're going to start with the rate question first, and then we'll get to the selectivity question. And recall that to do so, we need to compare the nucleophilicity of the two different aromatic compounds. And when we're comparing nucleophilicity within the context of these aromatic rings, we're really comparing the difference in how electron rich these different substrates are. So the first thing we should look at, since we already established it for toluene, is induction. And we've established for toluene that the dipole actually moves towards the benzene ring, which means that the methyl group on your benzene is inductively donating. But for your methoxy group, that CO bond is certainly going to be withdrawing electron density from the ring given the difference in electronegativity, which means that your methoxy group in anisole is actually inductively withdrawing. So it's withdrawing electron density from the benzene ring, which is not what we should expect, because if the anisole is faster, we should expect that the methoxy group ends up donating electron density to the ring. But according to induction, it's actually withdrawing electron density from the ring. So there must be something else that is going to be contributing to this particular reaction that we're not considering just yet. And the other argument that is stronger in most cases than induction is resonance. And for toluene, the methyl group does not do anything when it comes to resonance. Of course, there's no lone pair or NTP orbital to affect resonance in any way, shape, or form with that aromatic ring. However, for anisole, there is a lone pair on that oxygen that can donate electron density to the ring. So here's one resonance pattern that you should be able to draw out, right? And then you can keep going. That's another resonance form. And then here's the last resonance form. Okay. And note that if you keep going, you will end up with the exact same structure in the very beginning. But note that if you think about the resonance forms here, let's draw the resonance hybrid of this molecule. So consider the resonance hybrid of anisole. Note that the methoxy group in anisole effectively donate electron density to the ring. And that's really important because although the methoxy group is inductively withdrawing, it's actually resonance donating, which would then make that ring significantly activated towards electrophilic aromatic substitution. Okay, so it's actually the resonance effect that's going to override the inductive effect, which would make that methoxy group significantly more activated towards electrophilic aromatic substitution than the methyl group in your toluene. Okay, so we've just described why the methoxy group on your anisole is going to be activating the ring, or is going to be a really strong activator towards electrophilic aromatic substitution. Now let's describe why the methoxy group on anisole is ortho-para directing. In other words, why do you get more ortho and para products than the meta product? And once again, it all stems from that rate determining step, the formation of the sigma complex, because that's the step in which you add the nitro group to your aromatic ring. So once again, there are three possible sigma complexes, one in which the nitro group is ortho, one in which the nitro group is meta, and then one in which the nitro group is para. When the nitro group is ortho to the methoxy, we see that we can once again draw three different resonance forms where we essentially move that carbocation character around the ring. However, there is a fourth resonance form that we can absolutely draw here, and this one is going to involve that methoxy oxygen. So I've circled this just so you know that in the ortho case is an extra resonance form that we need to focus on. Let's look at the para case first, and then we'll get to the meta. In the para case, once again, you can envision three sigma complex resonance forms where, once again, you can just move the double bond around the ring, which would then move the carbocation character around the ring as well. But there's a fourth resonance form you can also draw here, which essentially comes from the methoxy group lone pair, once again, donating electron density into the ring and further spreading that carbocation towards the oxygen. So once again, I'm going to circle out that extra resonance form that we've drawn when the nitro group adds in the ortho and the para position. Okay, so now consider the sigma complex when the nitro group adds the meta position. So I have drawn all three of those sigma complexes that we're used to seeing. However, note that there's actually no way in this particular case where you could draw another resonance form in which the methoxy group takes that positive charge away from the aromatic ring. So we say that in this particular reaction, there are additional resonance forms in the ortho and the para complexes that are stabilizing the sigma complex, and so more of the ortho para products will be formed in this reaction. And so therefore, we say that the alkoxy groups, or the methoxy group specifically in anisole, is orthoparadirectin. So now we will consider the opposite effect where a group may potentially deactivate a ring towards electrophilic aromatic substitutions. So recall that activating groups or activators, they donate electron density to the benzene ring, which would then make that ring more electron rich and then make it more reactive towards electrophilic aromatic substitutions. On the other hand, you could then explain that a deactivating group or a deactivator would withdraw electron density from that benzene ring, which would then make it more electron poor, and therefore it will be less reactive towards electrophilic aromatic substitutions. For example, consider nitrobenzene and consider the nitration of nitrobenzene. It turns out this reaction is actually 100,000 times less reactive towards electrophilic aromatic substitution than the corresponding nitration reaction with benzene. So that's remarkable. In addition, the reaction is very much regioselective, but it's not regioselective towards the ortho or the para products like we've seen in the previous cases with the activators. This time, we actually observed that the selectivity goes towards the meta product as opposed to the ortho or the para products. Okay, so let's first try to explain why the rate is so much slower, so much smaller than with benzene. The first thing we look at is induction. So consider the nitro group on your benzene ring. It's pretty clear that the nitro group is going to be withdrawing electron density from that benzene ring. Once again, if you just focus on the dipole moment between the carbon and nitrogen bond, you would see that that's going to be inductively withdrawing. In addition, it's even more inductively withdrawn because that nitrogen is already electron deficient. It has that positive charge on it, which would mean that it really wants electrons. It's going to be trying to pull electron density away from that ring even more. So we consider this nitro group inductively withdrawing, which would then serve to deactivate the ring. It turns out our resonance can also explain why the nitro group is a specifically strong deactivating group. So consider the resonance forms that I have drawn here for your nitrobenzene. In all these cases, the electron density is being withdrawn from the ring through resonance. So we say that the nitro group is both inductively withdrawing, but also resonance withdrawing as well. Okay, and then the next question to answer is, so why is the nitrobenzene reaction selective towards the formation of your meta product over your ortho or your para product? As we can see, 93% of the product is actually going to be your meta nitrated nitrobenzene. And so once again, we must consider the selectivity determinant step as well as the rate determinant step, which is the formation of your sigma complex. So once again, the nitro group can add ortho, meta, or para with respect to the other nitro group on the ring. And I have gone ahead to draw out all three of those sigma complexes, whether it's ortho, meta, or para. Please take a moment here to pause the video and really observe all three of these. Make sure you know how to derive the sigma complexes for all three of these cases. However, I have circled two resonance forms that are particularly bad. Note that in both of these resonance forms, there is a carbon with a positive charge that is adjacent to the nitrogen with that same positive charge. That's really bad. Remember that the nitro group is electron withdrawing, which means it's going to be withdrawing electron density from the ring. So the last thing it wants is for the carbon next to it to also be electron deficient, which is the case when you're drawing the sigma complexes leading to the ortho and the para products. Note that in no resonance form, when you're drawing the sigma complex into the meta product, do you have that positive charge placed directly at the carbon bearing that nitrogen. And so the sigma complexes leading to the ortho and the para products are actually very destabilized due to the proximal electron withdrawing group that is next to that positively charged carbon. And it's because there's a particular destabilization of the ortho and the para sigma complexes, by default, the meta complex is going to be more likely to occur, which means that those meta products are going to be more predominantly formed. And so therefore, we say that that nitro group is meta-directing because it would selectively nitrate or substitute at that meta position in order to avoid the extreme destabilization that comes from the ortho and the para sigma complexes. Okay, so my hope is that you're starting to see some kind of trend here. It seems like activating groups are also ortho-para directed. In other words, groups that donate electron density to the ring seem to also be selecting for the ortho and the para products in electrophilic aromatic substitutions. And on the other hand, deactivating groups are meta-directed. In other words, groups that would withdraw electron density from the ring seem to also direct substitution towards the meta position in the ring. And this is indeed going to be what you would observe for the majority of your electrophilic aromatic substitution reactions. Activating groups orthopara directing, deactivating groups meta directing. There is one important exception, however. Halogen, they happen to be orthopara directed, however, they are deactivators. So there's a mismatch here between the activating capacity of halogens and their directing capacity as well. So once again, we look at our factors, induction and resonance. But if you look at induction, we would see that, in fact, these halogens, such as your chlorobenzene, will absolutely withdraw electron density from the ring through induction, right? So the electronegativity difference will tell you that that chlorine is going to be withdrawing electron density from the entire aromatic ring. With regards to resonance, however, it turns out the chlorine, because it does have a lone pair, can indeed donate electron density towards the benzene ring, okay, which would make that benzene ring electron rich if you're looking at simply resonance. So we've come up with a conundrum here. So the induction argument seems to be consistent with the fact that halogens are deactivators, but the resonance argument seems to be inconsistent with the fact that halogens are deactivators. And typically, we've seen that resonance effects tend to override induction effect, such as in your anisole. We've seen that, yes, there is an induction resonance mismatch, but the resonance effect was overriding the induction. Halogens are the important exceptions. Just know that for halogen substituents, the induction argument overrides the resonance arguments in these cases. Okay, so there's like a way to actually classify activators and deactivators as weak, moderate, or strong. And those are going to be important when we start thinking about when we have more than one substituent on an aromatic ring, which of these substituents are going to take precedence in directing the further electrophilic aromatic substitutions. Okay, so here are examples of your strong activators. They have a pretty similar characteristic. They tend to have lone pairs adjacent to the aromatic ring that can donate electron density towards that aromatic ring. So you have your OH groups, your O minus, NH2, NHR, NR2, where your R equals to alkyl groups. And then for your moderately activating groups, they're fairly similar to the strong activating groups. However, the lone pairs that would typically donate electron density to the ring are also being involved in resonance that are outside the ring. So your ester, for example, you imagine that the lone pair on the oxygen connects to the aromatic ring can either donate electron density to the ring or donate electron density to the pi system, the carbonyl pi system outside of the ring. Same for your amides. And so that's why they're a little bit weaker as activators, but they still activate the ring absolutely. An exception to the rule is if you have your alkoxy group, so your anisole, for example, will be an example, that those who are considered moderate activators, even though there are no competing resonance forms outside of the ring. Okay, so be careful with the OR versus your OH. Your OH group is a strong activator, your OR is a moderate activator. For your weak activating groups, you simply have your alkyl groups. Okay, so now we get to the deactivating groups. So as we've just mentioned in the previous scene, your halides are deactivating groups. They're fairly weak as deactivating groups, however, and that's a lot because that chlorine, bromine, and iodine can still donate electron density through resonance. It just happens that the induction tends to override the resonance in these particular cases. There are several moderately deactivating groups that are very prevalent in our inorganic chemistry. Essentially, what you should look for is any substituent in which there's a pi bond to an electronegative atom. So you have your carbonyls, your esters, your carboxylic acids, and your amides. These are all going to be moderately deactivated because you can also imagine they're inductively withdrawing as well as resonance withdrawing as well. So all of those, but also including your sulfonates, your SO3H group is also moderately deactivated, and your nitrile, once again, pi bonds to an electronegative atom. And then lastly, your very strong deactivating groups. There's really not that much of a pattern here. However, a lot of these are very, very strongly inductively withdrawing. So it turns out the inductive effect in all these cases are really, really strong. So your nitro group we just talked about, that's pretty strongly deactivating. But same as your alkyl ammonium. So when you have your NR3 plus, that's going to be very, very, very deactivating on your ring. And lastly, if you have your CX3 group like CCl3, CBr3, and CF3 groups connected to your benzene ring, that's actually going to be very deactivating as well. So for these three, you need to be able to commit them to memory. The other ones you can kind of reason out by looking at the patterns on your activating and deactivating capacity. Okay, and as we've just talked about, activators are ortho-para-directing, and we talked about why that's the case. So it's not a surprise that all your activators that we mentioned are all going to be ortho-para-directing. However, there is a deactivator that's also ortho-para-directing, which are your halogens. So keep that in mind that that's your exception to the rule. And of course, as a general rule, your deactivators are meta-directing as well. So notice that your moderate and your strong deactivators are all meta-directing. Once again, the exception here is your halogen, which is a deactivator, but it's going to be ortho-para-directing. Okay, so this table is pretty important, and it's also in your textbook, but you should be able to know not just if something is going to be activating or deactivating, but also how strong of an activator is a particular group and how strong of a deactivator is a particular group. All right, so that's it for the video. We've been able to predict the major products for electrophilic aromatic substitutions of monosubstituted benzene rings. We've been able to explain why some groups are activators and some are deactivators. And then finally, we've been able to explain why activators are ortho-para-directing and deactivators are meta-directing in electrophilic aromatic substitutions. All right, thank you so much for watching this video, and I will see you in class.